In today's lecture, we're going to talk about performance profiling and optimization, with the immediate caveat that we're in dangerous territory. Luminaries such as these on the slide tell us that it is a near occasion of sin and to be avoided unless and until absolutely necessary. This is sort of the last stop on our Programming in the Large roadshow. We've seen topics related to design and implementation, debugging, and testing, primarily the development portion of software engineering. Now we'll see a topic related more to the maintenance phase of software engineering. Specifically, over time, it is often necessary to improve the performance of a program to fit changing requirements or emerging use cases. So with those luminaries warnings in mind, and more still to come, let's go ahead and look at some performance improvement techniques and tools. We'll want to focus on finding where in the program needs or could benefit from improvement using these tools, and then figure out what are fruitful avenues of approach to realizing that improvement, versus those avenues that either are unlikely to render any benefit or are likely to already be available from the compiler without our own intervention. Perhaps before we ask what we should optimize and how we should optimize it, we should heed those warnings and consider, should we optimize at all? On the plus side for optimization, there's getting your program to run faster. I probably don't need to say much about the merits of that. On the minus side, though, there are some considerations that you might not have thought of before. If you start with a perfectly good program in terms of style, design, readability, ease of maintenance, correctness, but one that is insufficient in terms of time performance, you'll probably have to change some of those good properties in order to fix the performance. That might mean unrolling loops and inlining function calls. That makes your code a mess of cloned code. That might mean putting variables in registers and never in memory at all. As we saw in last lecture, this could make for tricky debugging if you're focused on memory locations to track in GDB. And just like when you make any change at all to your code, and especially when trying to be smart or tricky, you're likely to break something. After all, there is what Linus Ackerson calls Kernahan's lever, referring to a passage in the second chapter of The Elements of Programming Style by Kernahan and Plugger. This is another great book. We don't use it simply because its examples come from Fortran and PL1, so it's a bit dated, but the pearls of wisdom are still true. Quoting that book, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? You of course know Kernahan as the author of the K&P book on this slide and a prof in the department. You perhaps don't know PJ Plugger, who is another prolific author of books about software engineering. He's a serial entrepreneur, has been a member of the C and C++ standard committees over the years. Away from tech, he's also an award-winning fiction author. And I mention him primarily because, naturally, he's a Princeton alum, class of 1965. So taking a page from another Kernahan treatise, this time the one suggested for this course's readings, we have yet another admonition. In particular, people should consider both computer cost and people cost. Computer cost is the cost in terms of time and space of compiling and executing your program. People cost is the cost of labor associated with developing and maintaining your program over time. In the general case, people cost is much more expensive than computer cost. Optimization reduces computer cost, but often makes the code less clear, and so it increases people cost. Sufficiently opaque optimization can turn your $200,000 per year developer back into that kid in Intro to Programming who finds out that, I don't understand why this doesn't work, has a sometimes even more dangerous relative. I don't understand why this does work. So in that case, where optimization may yield a net financial negative to your company, it is a compelling case that we should only do optimization when it is an absolute obvious necessity. That said, we will still teach you some techniques for doing so. Okay, so all the foreboding and scare tactics out of the way, let's move forward. The simplest thing you can do to see if your program takes too long is, well, time it. The time command is the Unix equivalent of taking a stopwatch to your code. It produces three outputs, the real, user, and system times, where the real time is that sort of stopwatch. It's the amount of time on the wall clock. The user time is the amount of time that the program is running on the system. And then the system time is the amount of time that we spend in the operating system having the operating system do something on our behalf. We'll talk later in this course about system calls, which are this asking the OS to do something for us, as we dive deeper into our services tour. Typically, we care most about the user time, but in some cases, a very high system time can indicate a problem of its own. The reason why we care more about user time is that real time, the wall clock time, can be higher than the user time. For example, a program may wait a long time for input, or it may be waiting on other processes if there's contention for the processor. In the example on this slide, it's no big deal. The input came from a file, so we didn't have to wait for somebody to type in all that data, and it was run basically alone on a machine. One way to get better performance is to ask the compiler to try and do it for you. Minus capital O, note the difference in capitalization from minus lowercase o, which specifies the name of the executable. Minus capital O has a ton of options of various granularities, ranging from a blanket, do some optimization for me, all the way down to, I am a compiler expert and I want you to turn on this specific type of optimization, but absolutely don't do that one. Here are some of the relatively high-level optimizations that we might use in A4 or A5 for this course. Minus O0 says don't optimize at all. Minus O1 says do some default level of optimization, all the way to minus O3 that starts to say, if you know about this as an optimization, try and do it. You might think, why is it not always better to build with optimization? Well, one reason is that the compiler will take slightly longer to run, but frankly, this isn't that big a deal in the grand scheme of things. However, when built with optimization, the program could make some of the optimizations we saw last time, where some of the variables might be in registers instead of memory. These variables could then not be examined using GDB. Our general suggestion is, as you develop, build without optimization. Once you're convinced your program works and is right, and you're ready to start tuning it to send to your customers, that's the time to build with optimization, if necessary. So you timed it, and yep, your clients were right. It takes much too long relative to their requirements. So what now? At this point, if it's taking too long, you need a bit more information than just the raw amount of time it took. It ran for 10 seconds isn't helpful. You need something more like, it ran for 10 seconds, 9 of which were in this function, so that you know that's a function to try and make faster. Or, this function was called millions of times, so that you know any small optimization in it would pay huge dividends. One level more fine-grained than how long does this program take would be how long does a function take? There's a library systime that has a bunch of time handling functions. For example, this code, you can ask, what time is it right now? That's the getTimeOfDay function. And then run some stuff. And then ask again, what time is it right now? With those two results, you can subtract one from the other. It's a bit awkward because the resolution shows both seconds and microseconds, so the calculation isn't pretty. But this would tell you how much wall clock time elapsed. There are two problems here. Number one, wall clock time might be artificially high relative to system time, like we talked about before. And number two, this actually wasn't defined in the C90 standard. Note that when we do get time of day, it will give us back a Unix time. You might have seen this called an epoch time, which is just the number of seconds that have elapsed since 0000 UTC, that's Greenwich Mean Time, on July 1st, 1970. This is a common paradigm for time in the Unix world. But if wall clock time doesn't work for us for either of those reasons, an alternative would be to measure CPU time. How many times did your computer clock tick while your function was running? The clock command measures this. So we can say start the clock and say clock. Then we'll do some stuff, end the clock at clock. This gives us, when we subtract, the number of clock ticks that have elapsed. But clock ticks aren't meaningful to us in human time, so we have to divide by the system parameter of clock ticks per second. That gives us human time. This is a better measure because it won't vary all that much based on system load or waiting on I/O, because the CPU time is frozen during these waits. Think of it as your code has to be actively running in order for it to remember to click the clock. So that's going to tell you how long this code took each time it was called, but you might also care about how many times it runs. The combination of those two will tell you how important this function is. The total time it runs across all calls is a metric that sort of combines these in terms of being interesting to optimize. Something that runs for a long time relative to other operations might be worth optimizing because it takes a long time. But this isn't necessarily true. Perhaps if it runs sufficiently rarely, then its total time is not significant and we won't care too much. Think about hash table expansion in A3. It's super slow, but we do it so rarely that it is dwarfed by the other operations, and we're willing to put up with it being slow. On the other hand, something that runs for a small time might still be worth optimizing because we do it so often. Thus, the total time is big. Further, when something that is very short but called often, there's a multiplier effect of more bang for your buck, of even small improvements. Concretely, consider saving 1 second from a function that runs once versus 1 millisecond from something that runs 100,000 times. The former is a 1 second saving, the latter is a 100 second saving. So a way we can get this information about how often functions are run is by using an execution profiler. The standard one in the GNU Linux platform is GPROF, for, well, GNU Profiler. GPROF was revolutionary. It appeared in SIGPlan PLDI, which is the premier programming languages conference, particularly as it relates to implementation in systems, back in 1982. And already by the end of the 80s, was already so mainstream that implementing a version of it was given as an assignment in this very course. It's now considered one of the 50 most influential PLDI papers of all time, and is credited with revolutionizing performance analysis as a field. To show off GPROF, let's use a really simple example program. It fills up an array with a bunch of random numbers, and then we sort that array. On this slide, you can see the code for the swap function from sort and the partition function, which is a key function that you may recognize from quicksort. If you're not familiar with quicksort, don't worry about it for this slide. This is just a driving example. Finally, here's the top-level quicksort method and the main function that populates the array and sorts it. Again, don't worry about the details of the algorithm. For one thing, this is obviously pretty artificial. We're filling with random data, and we're sorting the array, but then we're just returning without doing any output or any other manipulation of it. But it serves us well for demonstrating a computationally intensive function. So with this program, we want to dive in and see what in the program takes a long time. When we generate that report, it comes in a few different sections. We won't go through all of the details, but here's a general idea. The first table is the most interesting one. On each line is a function with corresponding information. The leftmost column is the big summary that shows what percentage of the total runtime was spent in each function, in descending order by amount. The third column is the total amount of time spent in that function across all calls to it. The second column is just a cumulative sum down that third column, and that lets us get the total percentage. The fourth column is the total number of calls for each function. The fifth column is a normalized amount of time spent specifically in each of those function calls as they're executing. Think of this as the third column divided by the fourth. What's different between the fifth and sixth columns is that the sixth column is a normalized amount of time for each of those function calls, but considering from the beginning to the end of the function. So it includes all of the time taken waiting for its descendants. This is how we can see quicksort doesn't take a whole lot of time actually processing within quicksort, but spends a lot of time waiting for its descendants to get back to it. GPROF also produces an even more complicated information about the trajectory of the program. You can think of it as describing the graph of the program. Each function is a graph node and each function call is a graph edge. This means we can see what functions call which other functions, and we can have weights to the graph based on how often this occurs. We won't worry too much about this for now. For our purposes, the first table is sufficient, though we will ask you to submit the entire report as part of assignment 4. So back to that first report, we can interpret it as such. Fill array is only called once and doesn't take much of the final time, so it's really not worth trying to optimize. Quicksort similarly doesn't seem to be the bottleneck. Its descendants do a lot of work, but it doesn't really do much itself. Swap is called a ton of times. In a program that lasts less than 3 seconds, it's called 55 million times. But each call is minuscule, and even altogether they add up to be less than 10% of the program. So even if we made it orders of magnitude faster to swap, the upside is still only about 10% gain. Amdahl's law suggests that this is perhaps worth looking at, but shouldn't be the primary target. Partition, on the other hand, takes up 85% of the program, so any improvement here could make a gigantic improvement to the program overall. And because there are still millions of calls to it, even a small improvement could prove impactful when multiplied out. So that was a crash course on how to run GPROF and how to interpret the results and what analysis you might start to do with those results. We'll ask you to do this on assignment 4. But once you know what the function is that you want to try to optimize, now you need some techniques for how to, in fact, do that. Certainly one option is to work smarter and use a better algorithm, either in terms of asymptotic efficiency or performance characteristics that are better tuned to the workloads that you intend to deal with. Unfortunately, better algorithms sometimes come at the cost of lesser readability, maintainability, or other qualities. All of this is sort of beside the point because algorithms and data structures are really the bailiwick of COS226, and so we won't focus on that here in COS217. Instead, let's think more observationally about our code. Let's try and find patterns in code that seem to beg for optimization because they have obvious repeated computation, or maybe subtle repeated computation. We'll try to use our special knowledge we've accumulated about what works and what idioms we should look for, both good and bad, and in particular knowledge of how this code may be used in an application. But as we do so, we should ask also, is this something that a clever compiler would be able to do for us? Because if it can, we should probably let it. Let's try some examples. Here we have a function g that returns f of x plus f of x plus f of x plus f of x. And our proposed optimization is instead to return 4 times the result of f of x once. Could the compiler do this optimization for you? Well, if we think about it, what we're really asking is, could the compiler always be sure that it's right? 1 plus 1 plus 1 plus 1 is always 4. But f of x isn't necessarily so simple as 1. What happens if f of x isn't deterministic? For example, it has some baked-in non-determinism like it has a random number calculation inside. Or what if f of x has a side effect? Consider if f were printf, or if it updated a global variable. This optimization would fundamentally change the way the code works by changing the number of times that f is called. On this slide, in the first case, the value of the counter would become 4, and in the second case, the value would become 1. Also, it would still return different values. If the compiler has access to f, maybe it can do some additional analysis to make a better call as to whether this optimization is safe. But in the general case, oftentimes the compiler will have functions that it knows exist, but it doesn't have the code for. And further, there's still lots of code out there that we can't magically analyze in this way. On the other hand, maybe you can analyze it in this way because you have more knowledge than the compiler. Maybe you wrote the code and have a really good sense of what it does or doesn't do with side effects. Or perhaps you can read the interface for f and read the contract established in the interface comments to see what the contract says it does in terms of input, output, or updating global structures. Here's another example. The computation n times I is invariant in the inner loop. It would be much more efficient to compute it in the outer loop instead. As always with these questions, I want you to stop the slides, think about the answer, see, can you convince yourself, is this safe? Could a compiler do this for us? Is it even correct in the first place? Once you've taken a stand, commit to writing it down to keep yourself honest that you've actually made a choice, then you can come back to the slide. In this case, the answer is probably yes. The compiler has the full information. It knows that nothing else is changing n or I, and it can figure out that it can pull the computation out into the outer loop, out of the inner loop, and do it only once. But it's still probably better to do it yourself. There's no mystery for you. If you can see it easily enough yourself, why leave it up to the compiler that you don't know whether it will do it or not? While we're on this slide, there's another optimization available here. Go ahead and pause the slide again and take a moment to look. Let's look at the values of ni. Normally, initially it's 0, then it's n, then it's 2n, then it's 3n. I is incrementing by 1 and n isn't changing. So one minor optimization we could do is, instead of redoing the multiplication each time through the loop, we could just add another n each time, accumulating with addition. Addition is typically faster than multiplication, so this could be another small optimization in how this snippet is written. A smart compiler could probably do this for us as well. Here's another one, pretty similar to the previous one. For each character in a string, we want to do something with it. But this code is inefficient. At each loop-sustaining condition check, we recompute the length of the string. Assuming that the string's length isn't being modified in the body, we shouldn't need to recompute it. Can the compiler do this for you? In answering this question, you need to figure out, what does the compiler need to know? Well, the compiler would need to know whether that string is being modified in the body, and what does strlen do? Just because strlen is part of the standard library doesn't mean that the compiler naturally knows what it does, and also doesn't mean that it doesn't have side effects. The compiler probably cannot do this optimization for you, but you certainly can. Because you wrote the code inside of the loop, you know whether you're modifying the string's length. And you do know what strlen does. You can go and read the man page and see that it doesn't list any side effects. So you can avoid this n squared performance hit that the compiler likely cannot. Here's yet another one to consider. Twiddle takes 2 pointers and adds the second integer it points to the first integer it points to. Then it does it again. Instead, could we use multiplication instead of repeated addition? Again, pause the slide, come up with an answer for yourself, convince yourself of your justification, and then come back. The compiler can't do this for you because it might not even be right. Suppose that P1 and P2 point to the same int in memory, and imagine that int has initial value 2. The first version, star P1 plus equals star P2, assigns 4 to that int. Star P1 plus equals star P2 again then will assign 8 to that int in memory. The second version, on the other hand, star P1 plus equals star P2 times 2 will assign 6 to that place in memory. So you could make this optimization if you have some guarantee that they'll not be aliases. But the compiler typically does not have this guarantee. Because of this, some later compilers, starting with C99, support the restrict keyword. We apply it to a pointer, int star restrict P1, assuring the compiler that the object referenced by P1 will be accessed only through P1. In that case, the compiler would feel free to do this optimization shown, but in C90 where we live, restrict isn't a thing, and so this is another optimization that you could do if you can make the recognition that they can never be aliases, but our compiler could not. Okay, so enough with the trick questions. I want to finish up this lecture with 2 more optimization techniques. We've always been told that there's overhead associated with calling a function. Now that we've just covered assembly language, you know exactly what that overhead is. We have to jump to a different part of the text section. We have to do our prologue, where we allocate memory for our stack and save the old x30. And we have our epilogue, where we restore the old x30 and tear down the stack. And we have to jump back to just after the original spot in the code. Inlining a function call eliminates that overhead. Inlining is just taking the body of the function and putting it directly into the code where the function call would have been. And then we adjust so that the parameters in the function body get instead the argument that would have gone in the function call. A good compiler can inline this call of G, but only if it has access to the definition of G, which we know it doesn't always. Again, some newer compilers, starting with C99, support the inline keyword, which basically lets the programmer provide a strong suggestion to the compiler that it should inline calls of this specific function when it can. Just as there's overhead associated with jumping into a function, there is for a loop as well. We have to do a compare instruction and a conditional jump instruction. Further, in advanced architectures, the processor may be working on multiple instructions at once. For example, executing instruction X, decoding instruction X plus 1, and fetching instruction X plus 2, all at the same time. But as part of this pipeline of instructions, the processor has to do branch prediction. When it gets to some non-deterministic point in the code, it has to guess which instruction will come next. Branch prediction can be wrong, and loops, for example, have the potential to trash this pipeline. If the processor guesses wrong, all the work it has done up till now filling this pipeline will not come to fruition, and so it's lost the investment of the pipeline in progress. These branch prediction misses dramatically slow down execution. Unrolling the loop, as seen here on the slide, adds more code to the body of the loop. That avoids some of this overhead because it processes more things unconditionally. So loop unrolling, in the right circumstances, can be advantageous. Some compilers do produce code that supports this. For example, GCC has a -f unroll loops command line option to implement a suggestion to the compiler that it should try to unroll loops whenever possible. Finally, we catch back up to what we've been focusing on in the last couple of weeks, scrapping the compiler altogether and writing your own code natively in a lower level language. For some of you, this sounds great. After all, we talked about how there are instructions that a compiler doesn't even know about and can't make use of, but we can do research through the ARM Developer's Guide or other architecture manuals, and we'll know how to utilize them to their greatest extent. But before you get too excited, remember, compilers have had decades of cutting-edge research go into their design. They're tremendously clever and fantastically detailed. Handwritten assembly language code could very well be slower than compiler-generated code, especially when the assembly is written somewhat naively and when the compiler is run with speed optimization activated. And that's exactly what we're seeing in Assignment 4. Even with a rather perfectly set up problem that we know exactly the pattern to exploit, and being told to do all the right things, it only gets us to about as good as the compiler. And as you're finding out now, it takes a phenomenal effort to actually best it. That being said, it's also very gratifying to be able to do so. So good luck in the challenge part. I hope you'll enjoy the puzzle aspect of trying to beat the compiler. So this was our last lecture dealing with the assembly language and performance portion of the downward tour, which culminates with Assignment 4 due next Tuesday. In the next lectures, we'll take the elevator down yet another level and talk about machine language, which will lead into Assignment 5.